when we're doing inference, either a confidence interval or a hypothesis test, one of the conditions that we have to check if we're trying to generalize to a population is that we need a big population. Okay, so I want to explain first of all why we do that and how we'll check for that. So here's an example. It says, suppose that Ben has 3 green balls, 2 red balls, and 4 yellow balls. What is the probability of selecting 2 yellow balls? So the answer to this question depends on one thing. Are we sampling with replacement or are we sampling without replacement? Okay, so first we'll do it with replacement. And what that means is we're going to select the first ball, put it back in, and then select again. So the probability that we get a yellow ball on the first try is 4 out of 9. 9 total possible balls. Okay. So if we put it back in and sample again, then the next time we draw, we have another 4/9 chance. So the probability that that happens and that happens, remember we multiply those probabilities, is 16 out of 81. Okay. Now let's do it if it meant without replacement. If it means without replacement, meaning we pick a ball, then just pick a ball again, then we have a 4/9 chance that we get a yellow ball the first time. And then the second time we draw, there's only 3 yellow balls left. So we took 1 yellow ball out. And there's only 8 balls left. So that probability is 12 out of 72. So let's look at these probabilities in the calculator. We have 16 out of 81. And we have 12 out of 72. So there's a pretty big difference in those two probabilities. In the probability of getting 2 yellow balls, it's a big difference of whether we did it with replacement or without replacement. Okay, so let's go to these standard deviation formulas, which we do when we're doing a confidence interval or a hypothesis test about the mean or a sample proportion. It also goes with a two means or 2 proportions. It's all used. Standard deviation formulas assume sampling with replacement. Okay, but actually we sample without replacement in the real world. Okay, so I'm show an example of that and show why, even though these formulas assume that we're doing with replacement, that it doesn't matter as long as we have a big population. So here's our example. It says, suppose there is a corporation with 50,000 men and 50,000 women. We want to select 2 individuals from the corporation. What is the probability that they are both female? So let's look at these 2 probabilities the same way we did last time. So the first time, with replacement, there's a 1/2 chance that there's a 50,000 divided by 100,000 is 1/2. And if we replace it, there's a 1/2. So we're looking at about 1/4. Okay. Now, if we do without replacement, which is what we're going to do in the real world when we're trying to select a sample, if we select one of these people from this corporation, we're not going to choose them again. We want 2 individuals. So that's why we're doing without replacement, and we're basically always doing without replacement. So if that's the case, there's still the first time there's a 1/2 chance that there's a woman or a female. And on the second choice, there is a 49,999 out of 99,999. So you may be able to see already, before we put this in the calculator, why it doesn't make a big difference. This fraction right here, because we're working with a large population, our population is 100,000 people. Since we're working with a large population, this probability is going to be very close to 1/2. So that means this probability is going to be close to 1/4. So let's illustrate that. So we have 49,999 divided by 99,999. Very close to 0.5. Multiply that by 0.5. And we get very, very close to 1/4, which would be 0.25. So this is what we got with replacement. This is what we get without replacement. Notice that it's very, very close. So that's why even if we're sampling without replacement, which we will be, as long as we have a big population, our answers will be close enough to the same. So what do we use to, just like with testing to see if it's if the sampling distribution is approximate normal, we have guidelines. Okay, so these guidelines, there's nothing, I guess I could say special about what this means is the population is at least 10 times bigger than your sample size. Okay, and we're saying that at that point, if it's at least 10 times as big as the sample size, then your probabilities are going to be pretty close to the same. So let's go back to the first example. Okay, and what we're saying here, we're sampling 2 people, and our population was 9. Okay, we had 9 balls. We're going to sample 2 of those balls. So it did make a big difference whether we sampled with replacement or whether we sampled without replacement. Notice that big N would have to be at least 20 if you're taking a sample size of size 2. So in this example, N is still 2. Little n is still 2, but big N is 100,000. You're taking a sample size of size 2 from a big population. Now this is much larger than 10 times, as you can see. But that's our guideline that we'll use, and that's the guideline that most people use. As long as your population is 10 times as large, then the probabilities are going to be really, really close, depending on, or it doesn't matter which one you use, sampling with replacement or sampling without replacement. Make sure that's it.